Welcome to Group 33's presentation. I'm David Che.
I'm Abdulrahim Arjumand.
I'm Pamela Yakora.
I'm Mohammed Anwar.
And I'm Calvin Lobo.
The average human heart pumps 5 liters per minute at rest and can pump up to 25 liters per minute while engaging in heavy exercise. An assumption is the heart and brain are the most important organs in the body, and they would not function properly if they were not receive enough blood. The weight of the brain and heart weigh in terms of body mass about 3%, yet both of these organs function non-stop and require at least 20% of the overall cardiac output to function properly. But can we estimate the likely flow rate of these blood vessels?
Our observations are the following. Piping systems in maximum tension to withstand fluid flow before they burst, water fountains where the water moves higher and lower periodically, plumbing where the heart acts as the pump. We hypothesize that the radius of the blood vessel is the main component affecting blood flow and that the blood vessel will rupture once stage 4 hypertension is reached.
There are several factors that determine the resistance of blood to flow in a blood vessel. These include the blood's viscosity, the length of the blood vessel, and the radius of the vessel itself. Depending on our diet and metabolic needs, some of these parameters can be changed to meet our body's requirements for oxygen and nutrients. The primary relationship governing our blood's resistance to flow is given by R equals 8 mu L over pi R raised to the 4th. From our knowledge of fluid mechanics, we know that flow rate is determined in terms of the pressure difference or pressure gradient between upstream and downstream, which in this case is a result of our heart beating, and the resistance to flow. By substituting our resistance equation into our flow rate equation, we come up with this relationship. Q equals pi R raised to the 4th times delta P over 8 mu L. And this equation is known as Poissier's equation, and it primarily states that flow rate is proportional to radius raised to the 4th. Poissier's equation has some assumptions, 2 of them being that the blood must be incompressible and the blood flow must be laminar or streamlined.
The heart and brain needs 20% of the cardiac output in order to function properly. We use the Poissier's equation to determine the minimum overpressure of the blood vessel in times of rest and physical activities.
As a conclusion, in the hypothesis we stated that the dominant factor affecting blood flow is the radius of the blood vessels. Hence, for a given blood pressure, increasing the radius of the blood vessel leads to a linear increase in tension. This implies that large arteries must have thicker walls than small arteries in order to withstand level of tension. Another conclusion is that the blood vessels will rupture once the stage 4 hypertension is reached, which is 180 mm mercury over 100 mm mercury. Using Poissier's equation, we determined that the minimum flow rate to be 59 till 89 cm cubic per beat. Credit goes to the Cleveland Clinic Heart Book, New York, Hypertensions by Michael Eichner and Eric Topol. Many people do not find out they have high blood pressure until they have problems with their heart, kidney, or brain. 2 ways to reduce the stress on the blood vessels are increasing physical activities and avoid food high in saturated fats.